So let's go for our final presentation, who will be made, I believe, by Igor Alvarenga. Igor, are you there?
Hello, I'm here.
Yeah, Igor is from
Good afternoon.
the Federal University of Rio de Janeiro, and he'll talk about DAGSec, a hybrid distributed ledger architecture for the secure management of the Internet of Things. So the InterSCity project has a strong group working with blockchain technologies in the Federal University of Rio de Janeiro, and Igor will present one of the ongoing projects that they have there. So please share your screen, Igor. Yes, we can see it.
Okay, I'll start the presentation.
Okay.
Thank you for attending this presentation. I am Igor Alvarenga and I will present the paper DAGSec, a hybrid distributed ledger architecture for the secure management of the Internet of Things.
We will start by taking a look at the current Internet of Things environment, where fifth-generation mobile broadband networks improved connectivity, latency, and bandwidth for the Internet of Things. This enables billions of IoT devices to deliver pervasive services at the edge of the network. This includes smart cities, smart industry, environmental monitoring, autonomous agriculture, e-health, just to cite a few. IoT devices from different manufacturers provide services from IoT service providers to IoT service users, and those are connected to a multi-access edge computing node that replicates in small scale and close to the users the network core functionality in order to improve application and quality of service. Furthermore, services are provided and data is aggregated using network functions provisioned by cloud operators and managed by the IoT service providers. When talking about the IoT environment challenges, the first thing that comes to mind when thinking about the fifth and sixth generation networks is that the environment is massive. We are talking about more than 20 billion devices exchanging more than 40 petabytes of daily data and ever-growing high throughput and low latency requirement for applications. At the same time, more than 70% of IoT devices contain vulnerabilities, neither authentication, configuration update, software update, and privacy through the leakage of user and device information. This brings us to our main research question, that is, how to create secure and auditable systems for the Internet of Things. One of the most well-explored answers in the literature today is to base system security on a distributed ledger technology, both for secure communication and secure data store. But when you slightly change the question into how to create secure and auditable systems for IoT while meeting fifth-generation networks throughput and latency requirements, this approach doesn't work so well anymore because distributed ledger solutions tend to have problems either on scalability or transaction throughput. When you talk about distributed ledgers, the first thing that comes to mind is blockchain. Blockchain is a structure composed by chained hashes that offers both ordering and chronology in a trusted form. Blockchain security properties are adequate to secure both cloud and Internet of Things systems, as extensively reviewed in the literature. But one thing about blockchains, that even if they are asynchronous when looking to the communication, they need to grow synchronously. That is, everybody needs to agree what will be the next block on the blockchain. This leads us to the well-known blockchain consensus bottleneck problem that affect in different ways the probabilistic consensus and deterministic consensus protocols. Probabilistic consensus enable a large number of participants because any number of participants may work on a valid block, but this leads to forking because more than one participant can discover a new block at the same round. So strategies like mining are employed in order to reduce overall network throughput, but enable the creation of a new block with a low chance of forking. This leads to raised resource consumption, and most proof of something protocols, like proof of stake, proof of work, or proof of burn, leads to resource wastage, either in the form of energy or in the form of tokens. Deterministic consensus protocols, on the other side, enable high transaction throughput with low resource consumption. But as the communication requirements are stringent, because you need a quadratic message exchange and a cubic message size based on the number of the participants that you have on consensus, you can only have so few participants, and this leads to low scalability systems. This motivates other approaches to be studied on the literature. One of such approaches is the direct Acyclic Graph, or DAG. DAGs, much like blockchains, are hash-linked structures. The main difference is that each unit in a DAG can link to one or more units instead of the single chain. DAGs are also partitionable data structures, because different nodes may have different views of the complete DAG. A node may be missing some of the units. But this leads us to high transaction throughput, because both unit creation and validation can happen in parallel. So the more members you have, the more validators you have. DAGs also present the same security properties that make blockchain suitable to securing distributed systems both on the clouds and on IoT networks. But a main difference between blockchain and DAGs is that DAGs grows asynchronously. This leads us to the DAG chronology problem, because we cannot be sure if the timestamp contained in the unity is the truth. The situation evolves on the more general DAG ordering problem, because for units that are not directly linked, the network perceives their creation time as a possible interval, and we can only have partial order when these intervals are not overlapping. When we have overlapping intervals, like the situation between unit 2 and unit 3, we cannot affirm anymore with certainty which unit precedes the other. Then, our proposal is a hybrid distributed ledger architecture based on DAGs for transaction storage and dissemination that offer us high transaction throughput, low latency, there is the same latency as network communication, and low resource consumption. And we will also propose a witness system based on a blockchain ledger that's responsible for ordering and chronology of DAG units. This system will only store the perceived unit creation time, but will not affect in any way unit creation nor dictate unit validation. This is very important to us because we want to maintain full individual user autonomy on transaction validation, avoiding the common pitfalls like special user or node cases who dictates what's the truth of the system. Our proposed architecture is composed of 5 modules that integrate themselves on the large architecture defined for multi-access computing by the European Telecommunication Standard Institute. We have 2 types of modules, client modules and ledger modules. Ledger modules function is to store the ledger, while client modules offer different ways to interact with the system. There is a user module targeted at manufacturers and IoT service providers that allows for interactive action in sending command, making requests, receiving and storing data, and so on. There are autonomous modules that are targeted to devices and virtual network functions. These modules operate on the device and respond from requests by the user modules. And there are the service modules that makes the bridge between cloud and edge services and the DAG. A user may request provisioning and other features from the service providers and infrastructure providers by means of communication with this module. Our proposed architecture works in 3 main fronts. One of them is to provide orchestration management with auditability and authentication to all messages exchanged between device manufacturers and IoT service providers and virtual machine, container, or an IoT cloud platforms. The second front is to offer configuration and update management to all users, where updates can be done privately and the authenticity of the update can be verified. The third front is storage management, where we want to guarantee that the sensor data is immutable and is also highly available both in public and private databases. We propose a transaction model where all requests, responses, and announcements are transactions on DAG units. DAG units are made on by GOSP, but are also sent directly to interested parties. In this way, the delay in communication is the same that was before the introduction of the DAG. Clients create and send units containing their own transactions. They do this in parallel and completely asynchronous fashion. Each client has a local view of the DAG and validation the transactions based on this view and its own rules. A client may request units from other clients and may request order and chronology information from a witness federation. In our work, we introduce the concept of witness as a special kind of node whose sole purpose is to observe the DAG and approximate the unit creation time by the time that the unit was first seen by the network. Witnesses are organized in federations, composed by either public or private bodies, and they store data for future auditioning of DAG transactions. Each federation is divided to serve as a witness to a specific group of DAG applications, and not the entire DAG. This way we will have multiple federations, conferring higher scalability to the overall architecture. And also, independent witnessing bodies looking at the same DAG application can keep each other in check, because a client may decide to forego of a witness federation if it is misbehaving. Clients decide in what federation they trust and for what purpose. This further improves scalability and further decentralizes the governance of the network. Witnesses store the transactions on a blockchain, and their activity occurs in parallel to DAG, becoming non-blocking for both DAG unit creation and DAG unit validation. They maintain consensus with other federation members, and because these members are well known, we use a deterministic consensus protocol, such as PBFT. The consensus around the data is also kept in the blockchain for witness auditing purposes. A witness transaction is composed by the unit hash, unit author, and the witnessing time. No kind of validation is performed by a witness in a DAG unit. It indicates when a witness first becomes aware of a unit, makes all other witnesses aware of this unit, and sets an upper limit for when a unit was created. We propose that witnessing time is set to the oldest time the majority of the witnesses can agree on. Also, witnesses can become aware of a unit during consensus, and in this case, the witnessing time will be equal to the block creation time for those units. If we still have a tie between independent units, the transaction with the most independent observations will take precedence over the other. And if we still have a tie, we will use the hash-based algorithm to differentiate on which unit precedes which. In conclusion, DAGSec design enables high scalability and low latency on envisioned IoT scenarios. Because DAGSec is built in a way that decouples unit creation and validation from unit ordering, DAGSec is the first DAG-based proposal that allows unit creation, validation, and ordering with a restricted local view of the DAG and full validation criteria based just on user. This further improves scalability because, different from other proposals, DAGSec doesn't have the need for global synchronization of the DAG. Our current and future work consists on implementation and extensive evaluation of DAGSec performance, while at the same time looking into the implementation of smart contracts, tokens, sharding, and payment channels. Thank you for your attention, and any questions can be directed to the email on the paper.
Thank you for attending this presentation. I am Igor Alvarenga, and I will present the paper DAGSec.
Stop. Okay, Igor, thank you for the presentation. We have a question from Professor Daniel Batista, who is in Campinas, I guess. Daniel, you can say speak your question, can you? Now he's looking for, no microphone. Okay, so I will read. On slide 17, Igor, what would be dedicated networks at the right side of the figure? Is it a 5G slice? Igor?
I'm taking a look on slide 17. The dedicated networks are the infrastructure provider networks that make the connection between the cloud and the MAC nodes on the architecture provided by ETSI.
Okay. Is that okay?
They are different from the internet because they are like the backbone of the internet. There is internet going through these connections also.
So Daniel is asking if there's no need for a 5G slice then.
I didn't understand the question.
He's asking if you need a 5G slice or not.
I believe there are 5G slices because this is the main architecture over which 5G is built.
Okay. Okay, I have a question, just a more generic question. As you mentioned, the IoT landscape nowadays, there's a big problem of security and privacy with most of the devices open on the internet and easily attacked. What do you believe? First, do you believe that in the future, this landscape will change? We'll have a more or less secure IoT landscape, and what will be required to that? We need more technology, or we need change in the law, change in the requirements for manufacturers?
We already some changes in the law with the GDPR, and I believe manufacturers will change their behavior because the problem with security is just that it's most of the times it's ignored by the manufacturers. I believe now that there's a high preoccupation with privacy and not leaking sensitive data, this kind of behavior will change. Also, most of IoT devices today, except some small sensors, have cryptographic capabilities. So it's possible to secure the communication in a way that was not so possible before.
Okay, so you think that things are changing in that regard?
Yes.
Yeah, because I think this will be essential for IoT to be adopted in a healthy way, right? To have both privacy and security incorporated. Okay, thank you very much. So with that, we come to the end of this year's InterSCity workshop. We hope next year to be in presence either here or somewhere else. We are here at the University of São Paulo, and hope to see you around. I remind you that InterSCity has still at least 2 years to go, and we have opportunities for master's, PhD, and postdoc students, and also for national and international collaborations on high quality research. So if you are interested in working with us, collaborating with us in any of the topics that the project addresses, please get in touch with any of the project members and we'll be happy to work together. Okay, see you all next time. Thank you for coming.